Okay, I think we're live. Awesome. I forgot to say to bring some blue tack. If you can grab some blue tack, that would be epic. I also forgot to suggest like a pencil or something like that. But yeah, if you could grab some blue tack. Also, go and say hi. Like, go onto Facebook and say hi. Share this with at least 3 other people. Let's get some people here watching this. I will be with you in uno momento. I already did. So I do a live with a group on a Friday morning, and I've already done the whole being muted thing. So I need to check that again, which is good. Got that song stuck in my head. Yes, I have put a post up. Woohoo! Well done me. Hi, Jake and Charlie. I can see you guys are there. Woohoo! Hi. Alright, I just need to go to the loo. I'll be back in 5. Well, less than 5. See how long it takes me. Okay, good morning, Matsmob. How are we doing? I've got you all tangled. You're so tangled in wires. How's things going? We're doing Galaxies today. I've just had the most epic session all about patterns on my puzzles and problems. I am absolutely buzzing for maths this morning. How about you? Are you ready? We're going to be looking at galaxies, which are friggin' massive. They are huge. And because they're so massive, we actually can't measure them in the same ways we do like things that we do on Earth. So let's start off. Like, I can visualize, where's my ruler? I can visualize a few different sort of measurements, for example. So I can visualize like a millimeter and a centimeter, even like an inch, because they tend to come up on rulers. So I can look at them and go, yeah. So an inch. It was meant to be around the size, I think, was it meant to be the length of the thumb? It seems very short. Oh, no, it was the knuckle to the end of a thumb, wasn't it? An inch. So an inch was meant to be the length from the knuckle bit to the end of a man's thumb. I mean, mine's nowhere near an inch, but that was where inches came from. Then we standardized everything, and we came down to like millimeters and centimeters that are all related by multiplying by tens, hundreds, thousands, things like that. So I can visualize those. I can visualize a centimeter, a millimeter, an inch. I can visualize a meter, like it's roughly how far you step, a meter. I can even look. So we live near the beach, and you can look out into the sea. We can see up into Scotland from where we live as well. Like I can visualize things like a mile and a kilometer, because I can see that far, or at least I've had a map and I've walked that sort of distance, or I've been in a car and I can visualize that sort of distance. So those things, they seem like tangible, like I can grab them, I can touch them, I can really understand them. Problem is, when we start looking up into space, things get big, and they get big quickly. And these things are so hard to wrap your head around the size of them, because they get so big so fast, and it's sort of like mind-blowing stuff. It reminds me of, so what frequently happens when you talk about big numbers is things, and I do this myself. So like a million, I can't really visualize a million of something. So if I'm thinking like £1 million, if I had £1 million coins, what does that even look like? It would be a lot. I'm aware of that. We're actually born just knowing how to recognize certain numbers, even animals, and they just instinctively recognize like 1, 2, 3, even 4, but then it just they sort of recognize those numbers, and then it's big. It's big or a lot after that. And that's like what a million is to me. I can recognize more numbers than 3 or 4, but a million, it's just big, it's a lot. And then that can sometimes get confused with a billion. I might just talk about it like, oh yeah, they might have 1 million of this, 1 billion of that, but actually the reality is a billion is 1,000 times more than a million. So it's like comparing £1 to £1,000. These numbers actually do have meaning. It's just that it's so massive. It's hard to wrap our head around, because we've never like held a million or a billion things that we can see. Like you probably do have millions or billions of things on your skin, but you just can't see them. So we have to invent different units to be able to talk about these absolutely massive things, which is kind of what today's about. And also about, like just looking at cool things in space, which is also awesome. Okay, so let's have a look at this bit. Let's start with Earth to the sun. Earth to the sun. Already, I think just thinking about the size of the Earth is pretty mind-blowing. We can measure it in miles and kilometers, but I'm not an astronaut. I've not been up in space and seen the Earth myself, like the whole of the Earth. So it's still pretty hard to wrap my head around. I know I've seen photos, but it's very different to actually seeing it for yourself, isn't it? So the distance from the Earth to the sun, we've talked about this before, about how it's not a set distance. The Earth doesn't go around the sun in a circle. So we talk about an average distance, and the average distance from the Earth to the sun, you can measure it in miles and kilometers and things like that. You can do it through looking at how long it takes light to pass between them. You can do calculations, but there's a standard unit, and it's called an astronomical unit. So rather than using this massive number for the distance between Earth and sun, they decided, right, let's decide that distance is a unit in itself. A bit like when we talked about an inch being the length of a man's thumb. They sort of said, right, let's make this unit something we can measure massive things in space. Now, that astronomical unit is actually around 150 million kilometers. It's more precise than that, actually. It's actually this number down here. Do you want to see it? 149,597,870.7 kilometers. Okay, but we can say I'm a mathematician. Sometimes I'm accurate, and other times I'm not. Like, let's make that about 150 million. Now, I'm not going to go into the next bit in too much detail, but if you are interested, I did do a bit on standard form, which is what I'm going to talk about here in some lessons in my multiplying in number sense. So you can look up the video for that. But standard index form is a way we can write massive numbers down, and it makes it a little bit easier to write them and record them, essentially. So the standard bit is taking a number between 1 and 10. So no bigger than 10, no smaller than 1. And then we say we're going to multiply it by 10 so many times. So in this case here, we can keep dividing 150 million by 10. And when you, I shouldn't say this, but essentially you're like removing zeros. When we divide it by 10, 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 and we keep doing that until we get to a number that is between 1 and 10. So 15 isn't between 1 and 10, but if I put a decimal point between the 1 and 5, 1.5 is between 1 and 10. Well, we'd have to multiply 1.5 by 10 8 times to make 150 million. Okay, so this is a way of writing very large numbers in a little bit easier way. And we are going to do a little bit. We can use our calculator for some of this today, and we might try and do that. But essentially, even that gets really challenging when we're talking about distances in galaxies. Okay, so we know that. So if I just flick back a second, here, the distance between the Earth and the Sun, we know it in kilometers. It's an average distance, but we've decided now that actually we're just going to call that 1 astronomical unit so that we can simplify things a bit. Okay, now let's just have a look inside our solar system. So we taught, I think last week, about the meteor belt that goes around the sun, and this is like our inner solar system from the sun out to Jupiter. Okay, and that in itself is 5 astronomical units. Okay, so just like 5 times the distance from us on Earth to the sun. I mean, just like even wrapping your head around that in itself. We can see Jupiter with the naked eye. You could go outside tonight. It's looking quite cloudy at the moment, but if it clears up this evening, you could go outside tonight and there's a good chance you'd be able to see it with your naked eye. Okay, but that's 5 times the distance from Earth to the sun. It's not from us to there, from between Jupiter and the sun. Right, so these things are massive distances away. We can work it out in kilometers, so you can actually do this in your calculator. We can take our number for an astronomical unit. So I'm going to take just the 150 million because it's easier to type in. So you're going to put 15. Oh no, we need to turn the calculator on first. 150, so 150, and then million is 6 zeros. So I need to type 1, 2, 3, 4, 5, 6. We're going to multiply that by 5, and that gives us our distance from Sun to Jupiter. So that's our inner solar system. You end up with this massive number. I don't know if you're going to be able to see it on there very well, if it's going to focus in very well, but if you've got a calculator, you can put that calculation in. And we've got 1, 2, 3, 4, 5, 6, 7 zeros. So that's 750 million kilometers. Okay, so bear that in mind. We're still in the millions at the moment, millions of kilometers. Okay. Now we're going to go further. We've not reached the edge of our solar system. That's just the inner part, the actual inner part of our solar system. Okay, so last week we also talked about comets, and most comets that we see from Earth come from the Kuiper. I think I'm saying that right, Kuiper belt, and that you found Pluto in there as well. Pluto was a planet when I was little. Nowadays it's not, because it's in this belt here where there's lots of comets and bits of ice and debris and stuff, so it's not cleared its path around the sun. If you're going from the edge of the sun to the edge of the Kuiper belt, you're talking 30 to 50 astronomical units. 30 to 50 astronomical units. So just to put that into context, that's 10 times more. So this 50 astronomical units, that's 10 times more than that inner solar system. So if you've still got that number on your calculator, 750 million, you need to now multiply that by 10. So we're multiplying that by 10. So we're now in the billions of kilometers away. So I've got 7 billion, I believe it is. Let me just check how many zeros I've got. Yeah, 7,500,000,000 kilometers away. What? So you can start to see why we need these massive, massive units to be able to explain these distances. And we're still not there. We're not even on the edge of the solar system yet. We're not there because actually our solar system, so we're not talking about galaxies, we're still in our solar system, goes out to something called the Oort, I think it's Oort or Oort. I'm not sure how to pronounce it because I've read it in a book rather than watching a video. Unusual nowadays, I know. But Oort, I'm going to call it, stick with Oort cloud. So it's like lots of debris and stuff that is still going around our sun, but it's the gravitational pull from our sun, which is it's, I believe, the closest star, is so weak that the parts in the outer edge of the Oort cloud are affected by the gravitational pull from other bits in space, like other stars and other bits of matter within space. There's no actual distinct edge. But if we go all the way to the edge of the Oort cloud, so this is the edge, the very edge of our solar system. That is 100,000. Now, just get your head around this. 100,000. Imagine 100,000 objects. Like, take, say, for example, like a pound coin again. A pound coin. Imagine what it would look like if you had 100,000 of them. 100,000. So I'm already thinking that's quite a lot. Now, these AU, this was an astronomical unit. So that's the distance, the average distance from the Earth to the sun. So we've got 100,000 of those. 100,000 of those. So that's 100,150 millions. All right. To put that into a calculator, you would have to do 100,000. So 1 followed by 5 zeros. 1, 2, 3, 4, 5. Multiplied by 150 million. So 150, 150. And then 6 zeros. 1, 2, 3, 4, 5, 6. Lots of calculators are not going to be happy with that. Lots of them are going to just not be happy with that at all because it runs out of space on the display. Mine's a scientific one. It's gone into something standard index form now because it can't actually fit the number onto the calculator. It's saying it's 1.5 times 10, 13 times. So it's going to multiply that by 10, 13 times. That's how huge it is. Now, actually, when we get to galaxies, they're so vast and so big, even astronomical units were deemed too small a measurement to measure them. So we have to go into an even bigger form of measurement. Before we do that, let's talk about types of galaxies. So there's different types of galaxies. You may or may not be aware of these. Okay, so the first type that I think is probably the one I think of when I'm thinking about a galaxy is a spiral galaxy. So you've got this main body of mass in the center, very, very bright. Galaxies shine, they're really bright. You can see them in the universe, because a lot of the universe is like massive patches of dark, but you can actually see galaxies because it's a huge concentration of stars, and you can see there's a main body in the middle, so there's lots and lots of stars, and then there's swirls around the outside. So this is the spiral galaxy. You've got the main body with these arms swirling around on the outside. We're going to try and make our own version of one of these today. Okay, so we'll start that before I talk a bit more about galaxies. I said to bring some cards. It can be scrap card, it can be anything, but essentially you need to make a square of cards. Now, I realised when I was live on Tuesday doing this that my usual trick for making a square is to fold like a triangle and then cut it, but I don't want to fold it this time. So if it's not a perfect square, that's not a huge deal here. Okay, so what I'm going to do is try and make a rough square. Last time I tried roughly folding it, so I didn't make a crease and sort of guessing where I was going to cut it. I'm going to show you a slightly different tactic for this now. If you've got a ruler, this will work. If not, you can do the sort of roughly fold it over and find where it would be that you would make the triangle, and then make a line where you're going to cut it off. If you've got a square already, spot on, that's amazing. If not, I'm going to show you my new tactic today. This is what I'm going to do today. What I'm going to do is I'm going to, oh, how high can I make this? Stay there, stay. Okay, I'm going to measure the length along the bottom, the shortest side of my bit of card. Mine's 24 centimeters. I don't think it's a standard bit of card, I'll be honest. It's whatever I could find in the total carnage that was our conservatory earlier. Well, it still is total carnage, it's just I'm not in there anymore. So 20 foot, mine's 24 centimeters. So what I'm going to do is measure 24 centimeters up this side and put a little mark. I'm going to do the same on the other side. I'm going to measure 24 centimeters up this side and put a little mark. That's going to be, it's come off my table, so I have to be careful. And then I'm just going to use my ruler to join those two bits up. So I'm just going to draw across there. And that's going to give me my fourth side to my square. Now it looks a bit wonky. I don't think I've done that very well. Check I've actually measured 24 centimeters. Yep, that is 24. Maybe my face is just wonky rather than the card. Can that happen? Oh no, it is a bit off. It is a bit off. There we go. Can you have a wonky face? Oh, sometimes I just wish my mouth would stop. Right, there we go. So I'm going to cut that bit off to create a square once I've found my scissors. Okay, so I'm going to cut that bit off, but then I'm going to show you what I'm going to do next. What I want to do is I want to, from each corner, cut towards the center, but I'm not going to cut all the way in. All right, so I'll tell you what, don't do that bit yet. I'll show you because I'm paranoid. I'm going to tell you that I'm going to not explain it very well and you're going to go, no, I've got all the way in and it's all falling apart. So let me cut this bit off and then I'll show you that bit and then I'll rabbit at you about Galaxies for a little bit longer if you'll tolerate it. So for this bit, so I've got my square of cards and essentially I want to draw a cross on here, yeah? But my ruler won't go all the way across, so I'm going to do a bit of an estimate. I'm sort of going to draw into the centre. I better use a better pen that you can actually see. Let me get one out that you're going to be able to see. Okay, so go from one side. I'm going to draw into the centre, but not all the way to the centre. So that's about 13 centimetres. And I'll do the same from the other side. So it's about, should we say about, how can I put this? If I was going all the way across, I want to leave a gap that is about a quarter of the length in the middle. It doesn't, like I said, it's not an exact science, this. So I do that from all the corners. I'm drawing a diagonal line in that's roughly the same length on each side. So mine's 13 centimetres. If you've got a smaller one, do it smaller. Doesn't have to be exactly precise. I mean, it can be. But yeah, do you see how I've left it? There's a gap in the middle. And I'm going to cut along all of these. So you're going to cut along all of those lines. All right. So you get cutting whilst I have a little chat to you about Galaxies. So some of you may or may not know that the name of our galaxy is called the Milky Way. So we live on the Earth. Our Earth is in a solar system that revolves around the sun. So the sun is the star that is the center of our solar system, and everything in it, because it's the biggest body, it's got the most, can you say the most gravity? It's got the biggest gravitational pull. So things revolve around the sun. They orbit around it. Okay. And that's everything that's orbiting around the sun is within our solar system. And our solar system is just a tiny part of a massive galaxy called the Milky Way. Now, the Milky Way is not a spiral galaxy. It's a little bit like a spiral galaxy. I saw a really good explanation of it being a bit like two fried eggs. Can you imagine like a fried egg? You've got the white bit and then the yellow bubbly bit in the middle. Yeah, it's like one on top and one underneath. So there's this big bubble, and that's there's a lot of stars essentially and a lot of galaxies a lot of solar systems in the central bit, but it's elongated a bit. It's elongated, that central bit, and then there's the arms that create the spirals coming off of it. So ours is actually called a bar spiral galaxy. It's really hard to find a photo that I'm allowed to use and show you online of this, but yeah, sort of like there's a bigger a bar central bit, like a spiral galaxy, which is centralized around more of a blob or a point. Ours has got this bar bit. Okay, so ours is called the Milky Way, and it is so vast and so huge across that in fact, if we were to write it in kilometers, it would be 9.5 times 10 to the power of 17. That means we're times 9.5 times by 10 17 times to get it in kilometers. And as I said, that is such a huge number that they deemed astronomical units not big enough to describe that distance from one side to the other. And we use the unit light years, which I believe, although I haven't factually checked this, I believe I just got it from school, the distance light would travel in the space of a year. So that is absolutely humongous. To put it into context in terms of the units we've been talking about, 1 light year is actually over 63,000 astronomical units, 63,241 astronomical units. Okay, so that's 63,000 times the distance from Earth to the sun just for 1 light year. So we're going to have to do that 63,000 multiplied by 100,000 just to get 1 light year. I mean, that absolutely blows my mind, the size of that. Okay, right, so hopefully, let's come back to this. You've got something that looks like this. I call these, very technical language here, flappy bits. So we've got some flappy bits. And on each flappy bit, we're just going to go to, I'm not very good with my right and left, so just give me a sec here. We're going to go to the left-hand side of each flappy bit. And in the corner, on the left-hand side, we're going to make a little hole on each flappy bit, only on the left-hand side though, okay? So this is where I said, if you were here at the beginning, I said I forgot to say, bring some blue tack. You can use a rubber, anything that's a bit squishy really, because we're going to poke a hole in it. And then probably just a sharp pencil will do. So I'll show you what I do, how I do this. It's very technical, accurate stuff, this, you can probably imagine. I put a bit of blue tack underneath, okay? And then I'm going to put the left-hand corner of my flappy bit on there, and then I'm just going to poke a hole through. Oh, my pencil's not sharp enough. My pencil's not sharp enough. I need a sharper one. I broke a pen doing it last time, so I'm being quite careful. I don't want to break any more pens. There we go. There's a sharper one. That worked. So then I got a hole there, and then I'm going to twizzle it around. I'm going to do the same in the left-hand corner of the next one. So I'll end up with four of these holes. Oh no, I've blunted my pencil. How powerful is this card? Who knew card could be that strong? Maybe if I use a pen. Should I try it with a pen? So we need to make a hole in every corner. Yeah, pen's working better. There we go. But then I broke a pen last time. You just never know what's going to work, do you? To try everything. Trial and error. So I'm going to make one on the left-hand corner of all the flappy bits, like this, yeah? Left-hand corner of every flappy bit. So you've got 4 holes. And then we'll go to the very middle. So we want to find the very middle. Again, it's not an exact science here, but maybe if I sort of extend these lines so they're joining. I mean, mine aren't even, they're not brilliantly done. Mine aren't in line. And where they cross over will actually be the central point, won't it? So you see there, that central bit there. We're going to pop a little hole in there as well. Now, where have I put my blue tack? Here we go. Pop that underneath, and we need a hole in the center as well, like that, okay? Yeah, so 5 holes. You got that? 5 holes. One on the left-hand side. I've not done it on the left-hand side. I've done it on the right-hand side. I told you I didn't know my right from left. Oh, well, you've either done the same as me or different. It doesn't matter, as long as it's always on the same side. Oh, my left and right are so dire. Okay, so I've gone on the right hand side. You've probably done the left hand side because I've banged on about that quite a lot. You put a little hole on each corner of these flappy bits and then one in the middle. Okay. Yeah, so there are other types of galaxies. We're in the Milky Way. As I said, that's a bar spiral galaxy. So you've got like this bar-like bit in the middle with the swirly bits coming around. They're called arms. There's two major arms, so two really big ones. We're not in one of those. We're in one of the minor ones called the Orion arm. And we're about 27,000 light years from the center of our galaxy. So again, just absolutely huge units we're talking about. All right. So we're about 27,000 light years from the center. Oh yeah, now I need to do that bit. I'll talk to you quickly about elliptical galaxies. You do get other types of galaxies. So elliptical galaxies, there you can see they're more like a cluster around a central point. So yeah, so they form. It's sort of an oval sort of shape. Okay, and then you also get irregular galaxies. And this isn't actually a picture of a galaxy, it's a picture of a nebula, but I couldn't find, it's just showing the irregular shape of it. That's what I was trying to emphasize, the irregularity of the shape of it. Okay, so you do get different shaped galaxies, and ours is the bar spiral galaxy. What we're trying to create here is something to represent a bit of a spiral galaxy. So if you've got a split pen, this is where you're going to use it. If you haven't, you can just use something like a pencil or something to poke through all the holes. Essentially, we need to keep all the holes together. Okay, so do we want to do, oh no, we don't want to do the split pen just yet. I apologize. Before that, we need our other piece. I said like maybe a stronger piece of card or some paper folded together. I'm just using, can you see that from awesome books? We like buying secondhand books when we can't get hold of them in the library. I'm just using a strip of this. A strip of the same card would do, some folded paper, just something to hold this together, okay? So I'm just cutting, it's not an exact science at all. Cutting a strip off. And we're going to need to do a hole in this. I have to make a noise whilst I'm cutting. What sort of noise do you make? Do you ever do that thing where you're cutting wrapping paper and you're like, shh, and it feels amazing until you hit a snag and you're like, oh man. But yeah, this isn't that sort of cutting, is it? This is cutting. I'm sure you all know exactly what I'm talking about here. So yeah, this is my strip, and I need to make a hole near the top of this. Okay, so we're going to make a little hole near the top of this again with my pen. I'm just going to poke a hole in it because I need this to be joined to my split pin as well. Okay, now I'm going to sort of build this up in layers, if you can imagine some layers. So I take my split pin, and what I'm going to do, I'm going to take one flappy bit, one corner, and go to the back corner and poke my split pin through. Yeah, so I'm folding it and going to the back. Now I'm going to go around, I'm going to grab the next corner and put it underneath and pop the split pin through that one. So we're building up layers together. Then we go around again, get the next corner and pop my split pin through the next hole. If you're doing this with a pencil, you can just sort of poke it through them all. Yeah, you might need a bit of a bigger hole. Okay, and then last corner, poke that through the split pin through that one, and then I'm going to push it all together and poke my split pin. Can you see through there? Can you see that very well? The split pin is going to go through the back and come out the back. You see, it's come out the back there. And then once I've done that, then I get my strip of card and I'm going to just poke the split pin through there and separate it. And what we end up with, and then it depends on how strong your card is. If it's strong enough, you can sort of hold it up that way. If it's not, you dangle it down. And what we've created is, in my eyes, a bit of a spiral galaxy. Because can you see, we've got like this central point that everything is rotating or orbiting around. And these, we've got, look, our arms coming up, and we can decorate those. We can decorate those with planets and stars, because it will contain thousands and thousands of stars. And we can just draw those onto our galaxy, our spiral galaxy, all over. It looks like it's got chicken pox a little bit, doesn't it? Oh, so yeah, this is the one I did the other day. Look, you can see I've started decorating one of the arms here, just like that. And it's quite like normal spiral galaxies aren't as regular as this. This has got something we call mathematically rotational symmetry, i.e. as we rotate it around, we can create the same shape over and over again. So if you imagine that arm there is pointing out at the moment, as I rotate it 90 degrees or a quarter turn, I've got another arm pointing exactly the same. The spiral galaxies are not that regular. They probably will get more, I assume, maybe they get more regular as they go on. I'm not sure if the gravitational pull creates that or not. But yeah, they're not as perfectly regular as this. But it gives you the idea of it, of how it works, how we've got all these solar systems all around, all these different star systems and stars dotted around. And then they're all together in one huge galaxy. Orbiting around one massive central point. And often, I believe at the center of the Milky Way, which is a bar spiral galaxy, but I couldn't work out how to make this wider. They reckon there's a giant black hole in the central point that everything's going around. Cool. So yeah, if you finish that, like, send me a picture. I love seeing the pictures of what you've created. Please do feel free to pop it on there. And if you're on Facebook, give me a comment, say hi on Facebook, because I'll go on there in a second and say hi. But I love seeing your pictures as well. They're absolutely epic. Just to give you a chance to finish that, and go onto Facebook and say hi, I'll just do my little spiel about my Maths Mob memo. I totally wish I called this Messy Maths. So this comes through to the post to all my members. So if you're a triangle or square, you're going to get this. Approved by kids, because my kids did all these activities and enjoyed them. We didn't put the rubbish ones in, we only put the good ones in. And it's exploring fractals, which is an awesome area of maths that I absolutely love, all through hands-on activities and some puzzles and activities you can do at home. And I did put a little quiz in. But yeah, so that is my offering to you. This is how to create one of these fractal cards. Me and my son explored how to do that together, and then we popped that in. I totally forgot about Barbie. Blasting off. Oh well, celebrate. So that comes through to the post, any triangle or square. Along with my original Maths Mob Momo, just to introduce Maths Mob Monkey, and some nice, cool origami paper as well, as a little thank you. And then if you become a square, I create these workbooks each week. You don't have to print that. I printed this in A4 so you can see it, but A5 is absolutely brilliant as well. So this is ones for number sense. I do them for number sense and I do them for Maths in Motion too. And it gives you all the notes for the session, but also what I do, and people are really enjoying, is put in the back something that you might want to have a go at home to explore further. So some ideas of how you can explore further. It might be a link, it might be a fact file, it might be create a quiz, lots of different cool things like that as well. And you get those straight away to print off if you become a square. Okay, so I'm going to say hi to some people. I've promised that, haven't I? So give me a sec. Yeah, I've had to charge my phone. It wasn't happy with me. I don't know why I put a stupid voice on them. It's also not going to like doing this. Give me one sec. See if I can find some people to say hi to. Hopefully some of you are saying hi. Oh, go away, Bridget. I'm not a fan. Right, who have we got? Okay, right. So, Jake and Charlie, you said hi at the start, didn't you? I already said, but I'll say hi again, guys. I hope you managed to stick around for the whole thing. It was really, really nice to have you here today. That's awesome. Jacob! Hi, Jacob. Jacob, you're epic. You're here every lesson. You're so dedicated. So dedicated. I appreciate it. Who else have we got? Oh, Bella! Hi, Bella. I love that eyes on the end, which is awesome. Who else have we got? Oh, Aaron and Ruby. I've said Aaron and Ruby. I said before, I always have Aaron and Ruby in my session before, and then I have Aaron and Ruby again. It's lovely. I love having so many different people come in and just feeling like I'm connecting with you. It's really cool. Thanks for coming again, guys. It's really nice to see you here. Oh, Runa. Hi, Runa. You're back as well. Awesome. Thanks for coming back, Runa. Nice to see you here. Oh, you've given, wait a second. You're going out later and taking the booklet for the fractals. Epic. I hope you have a good time with it. Take some pictures. Let me know how it goes. I'd love to see them. Really love to see them. Oh, when you put the hole on the right, not the left, you could have turned it over. Oh, man. Bella. Oh, why didn't I think? Oh, Bella, could you just come and help me teach next time, please? Bella's so right. All I had to do was turn it over and the hole would have been on the left, wouldn't it? Oh, Bella. Bella. Do you want a job? Because I think I might have one for you. Wow. Okay, this is why I need live comments, isn't it? Because I don't think of things like that. You are spot on. Thank you. Oh, and you're loving the... Oh, thanks, Bella. That's so nice to hear. It is real, like, I love doing these lessons. So it's really cool to hear when people are enjoying them too. It's such awesome feedback. Okay, right. I'm going to refresh. So I refresh once just to check, see if anyone leaves any extra comments. So I will do one refresh. Now, I don't mean to like not say hi to people, but you know, we could spend all day refreshing. Facebook does what it does, doesn't it? You know what it's like. Oh man, what's he doing now? What are you doing now, Facebook? Come on, give me a chance. Okay. No, it's gone on to Reels instead. Good. Thanks, Facebook. Hello from Runa again. As in another Runa. Is this two different Runas, or have you gone over to a different account? I can't tell. Runa, tell me, is it a new Runa or is it the same Runa on a different account? This has confused my brain. Okay, yeah, I'm gonna I need to know if that's a different Runa or if Runa you're doing it from two different accounts. Let me know. I can't tell. Hello from Runa again. I think it's the same Runa. Oh, why has it put comments? They're so annoying. It just puts them in random orders. Ollie, I so nearly missed you, Ollie, because for some reason Facebook put your comment like in the middle of a load that I'd already said. Hi, Ollie. Hi. I'm so glad I didn't miss your comment there. Runa, I need to know. I'm going to have to refresh one more time because I need to know if it's the same Runa or not. That's important to me for some reason right now. Let me have a little look. Same Runa, different account. Okay. I was thinking, Runa is not the most common name. Surely, yeah. Okay, awesome. Thank you so much, guys. I really, really value your time. Love having you here. Do spread the word. Tell other people to come for joyful maths. And I will see you next week for the universe. Ooh, even bigger. I don't know why I'm doing this. It's because it expands, isn't it? Yeah, I'll go with it expands. Okay, I'm going to stop before I say something I regret. Bye.